Once again, it's early morning and I'm here recording during first block. I was going to do this yesterday, but Emma came and hung out with me for the afternoon, and now she is a probability expert, so if you need help, see Emma. Okay, we're going to start with the addition law of probability for the laws of probability. Venn diagrams are really helpful to visualize laws of probability. So if I do the probability of A plus B, that's the probability of A or B. We know that A or B is the probability of A plus the probability of B. There's a little problem in this situation because I have some overlap. If I were to calculate the probability of A plus B, here's A, and to that I'm going to add B. And as you can see, right here I have overlap. I've counted this area twice. So in order to rectify that, you have to subtract out one of those areas, and that's the probability of A and B, or A intersect B. So this is actually the addition law of probability. It's the probability of A plus the probability of B minus the probability of A and B. Generally, when we do A or B, there's no overlap, right? The probability of A or B is equal to 0 here because these two circles don't overlap. This is when they're mutually exclusive. And that's the kind of probability we've been doing so far. And that becomes the probability of A. The formula here still works, plus the probability of B minus 0 because this is 0. Okay, here's my example with a Venn diagram. Venn diagrams, again, are really useful for seeing the laws of probability. So the number of students in the class here are the 3 who are not taking chemistry or history, the 5 taking only chemistry, the 17 taking both, and the 4 taking just history, which gives me a total of 29 students altogether in the class. Students who study both subjects, that's just my overlap here. That is 17. Students who study at least one of the subjects. So that's the probability of chemistry or history. And so you can see that it's the probability of studying chemistry. Oh, let's write down the law first. The probability of chemistry plus the probability of history minus the probability of both of them. And that gives me, so the number of students who are studying just chemistry, is going to be 5 and 17. We can go ahead and answer this question right off the bat. 5 and 17 are 22. So the number of students studying chemistry is 22. The number of students studying just history is 17 and 4, which is 21. And then we need to subtract out that overlap. That is going to be 17 that study both, and that gives me 26. So that's the addition law of probability at work. In this case, who study at least one of the subjects, it might be easier to take the whole sample space, and there's only 3 students who don't. That is also 26. So sometimes it's easier to do things differently. All right, here's one for you to try. Stop the video, restart it when you're ready to check your answer. Okay, the number of students in the club, that's going to be 7, 15, 27, and 26. Gives me a grand total of 75, I believe. Students who play hockey is 26 and 27. Gives me a grand total of 53. Students who play both sports, easy. That one's just the overlap here. That's 27. Students who play neither sport, 7. And students who play at least one sport. So depending on how you choose to do this, you could do just 15 plus 27 plus 26. I think that's a good way, and that's 68. Or I think actually even better would be 75 minus 7, also 68. Or you could figure out how many play tennis, how many play history, and subtract the overlap. Okay, so mutually exclusive events. We'll draw that again. A box of chocolate contains 6 centers, 6 hard centers, so we'll call that H, and 12 chocolates with soft centers, we'll call that S. And we want to know if these are mutually exclusive, so the probability that they're hard, we have 6 that are hard and 12 that are soft. The probability that they're hard is going to be 6 out of 18, because we have 18 chocolates in total. And number 2, the probability that they're soft is 12 out of 18. The probability that they intersect is 0 out of 18. And the probability of the either one is 6 out of 18 plus 12 out of 18 minus 0, which gives me 18 out of 18, which is 1. So we can say that if events are mutually exclusive, that the probability of A intersect B equals 0, and the probability of A or B becomes the probability of A plus the probability of B minus 0, which is just the probability of A plus B. Okay, product law for independent events. If you have a Venn diagram on your thing, scratch it off. It doesn't live in this slide, it's an accident. So the probability of A intersect B just becomes the probability of A times the probability of B. That's for independent events. Just thought I'd mention that real quick. Conditional probability, that is the probability of an event happening given that event B has occurred, and that's written as the probability of A. This line right here means given. Looks like a division sign. And this is event B has already happened. There's a formula for that. It's the probability of A intersect B, right? That's A and B, so A times B, divided by the probability of B. So this is generally a case where more people have trouble with probability or the laws of probability. What's really happening here is, because this is conditional, we're reducing our regular sample size to the size of whatever B is, because B has happened. So we're reducing the sample space usually. All right, so here's an example. In a class of 260 seniors, all of these students are taking Spanish, chemistry, and math, except for 5 students who aren't taking either. And I want to find out the probability that they're taking chemistry, so the probability of chemistry, given that they are taking Spanish as well. Okay, so to illustrate that, that's going to equal the probability of chemistry and Spanish divided by the probability that they're taking Spanish. Right, this is my given, so it goes here, and then the intersection of the two goes up top. Well, let's look at the intersection. The intersection of chemistry and math, I'm going to change my color here, happens here and nowhere else. That's where the circle for so if I circle chemistry and I circle Spanish, there's my overlap. So that is my overlap, and I can add those in this case. Happens to be 18 out of 260 total, and I know that from up here. Okay, let's look at just the probability of taking Spanish now, because that's in my denominator. So the probability that they're taking Spanish is this bubble here, and if I wanted to add that up, that becomes 93, because I have to add all of this area out of 260. This is my new sample space because this has happened already, so I'm only taking the students that are studying chemistry because I know they're the ones from Spanish. So I'm going to go ahead and put that in the formula. So it becomes 18 out of 260 divided by 93 out of 260. And if you know something about fractions, you're going to reciprocate and multiply, and that becomes 18 over 93, because my 260s are just going to cancel out. So that's the probability that someone is taking chemistry given the fact that they are taking Spanish. Okay, here's an example for you to try. I have a class of 40 students, 34 like bananas, 22 like pineapples, and 2 dislike both fruits. I am going to relabel this so that it's not confusing. Bananas, I'm going to call this pineapples. And I have 2 that don't like either fruit, which leaves me 38 that like one or the other or both. When I add the 2 together, I get 18 extra. So that's the number that like both. All right, so the probability that someone likes both fruits, and this is a probability, so it should be a decimal or a fraction. Probability that they like both is here. So that's going to be 18 out of 40. Ooh, I lost my pen somewhere. Okay, hopefully my pen's back. All right, likes at least one fruit. So at least one fruit would be the probability of A or B, bananas or pineapples, which is going to be 34 out of 40 plus 22 out of 40, because that's the number or the probability that they like bananas. Here's the probability they like pineapples, and then we're going to subtract out the 18 over 40, which gives me a total of 38 out of 40. Or you could do 1 minus the 2 that don't, 2 out of 40 that don't. All right, C, likes bananas given that he or she likes pineapples. So that's the probability of bananas given that they like pineapples. Again, that's going to be the intersection between them. And we already found that. That's 18 out of 40. So bananas intersect with pineapples over the probability that they like pineapples. So bananas intersect pineapples is 18 out of 40, and the probability that they like pineapples is 22 out of 40 from the information in the beginning or from this part here. And that leaves me with 18 over 22, or 9 over 11. That's the probability that given that they like pineapples, that they like bananas too. Okay, now the other way, likes pineapples given that he or she likes bananas. So that's the probability of pineapple given banana. Again, the intersection is 18 over 40, and then we're going to divide by the given, which is that they like bananas, and 34 out of 40 like bananas. So that gives me 18 over 34, which ends up being 9 over 22. Yes? No. 9 over 17. Blah. Bad math. Okay. So there's a number of ways that you can look at conditional probability. Here's a tree diagram. I want you to fill this out, and then I want you to calculate or find the probability that the tested adult is allergic to nuts given that the liquid is turned blue. So you're going to use the same formula. You're going to find the probability that the liquid turned blue, and you're going to use that to divide the probability that the tested adult is. You're going to find the intersection between the tested adult and the fact that the liquid turned blue, and divide it by that. All right. Pause this, restart it when you're ready. Okay, so we can go ahead and fill in that 0.994 are not allergic to nuts because this branch of the tree here has to equal 1. And then this would be 0.02 because this individual little branch would need to equal 1. And then the correct test results for 95% of people who are not allergic to nuts. So here's the tricky part. This is the correct result for people who are not allergic to nuts, and 5% of people who are not allergic to nuts, theirs still turns blue. So this is the intersection here, probability of allergic to nuts and blue. And that is 0.006 times 0.98, which results in 0.00588. Need a calculator for that. Okay, so here's the other spot that would be in the probability of blue. It could be this value or this value is where the blue happens. So I'm going to calculate this probability. So this is not allergic to nuts, but also turns blue. And that's 0.994 times 0.05. And that results in 0.0497. So that happens a little more frequently. All right, so the probability of blue is either this or this. So it's, if I add these two numbers together, I'm going to add them, I get 0.05558. All right, all that's left is this, the intersection. So the probability that that they're allergic, given that the liquid has turned blue, is going to be the intersection divided by the probability that it's blue, which gives me a value of 0.1058. So about 10.5% of the time, if they're allergic to nuts, that people are allergic to nuts if the test has turned blue, which means you have a lot of false positives. Okay, one more example from a table. I find this one actually the easiest way to do conditional probability because it's just intuitive, but I want you to take the information given here, fill in the table, and then find that probability that the person doesn't support that. What's the probability to the 100th that a person is 31 to 50 years old if they support the new school building. So it's the probability of 31 to 50 given that they support the school. Go ahead and pause this and restart it when you're ready. Okay, so 61 18 to 30 years old support it. The number of 31 to 50-year-olds that took the survey was 197. 103 of the 31 to 50-year-olds support the new building. 132 people 51 and older do not support the new building. And overall, a total of 240 people do not support the new building. And a total of 503 participated in the survey. Okay, so I don't have all the information, but I do have that the complete and total number of people is 503. So I can figure out the total that support the building from that by subtracting 240 from 503, and that gives me 263. And then from there, I can calculate the number of 51-year-olds that support it, the 51 and older. And so I need this column here to total 263, which means 99 of these people support it. And from there, I can calculate the total of 51 years and older who were surveyed by adding 99 and 132, and that gives me 231. And then I can calculate the total of 18 to 30 years olds, because again, my total is 503, so I need 75 more people to total that. And then that leaves me with the number of 18 to 30-year-olds who do not support the building is 14, and then there are 44 31 to 50-year-olds. So from a table, the probability of 31 to 50, not P, 50 intersect support divided by the probability that they support, because it's given that they support, that total is 263. And the intersection between the two, so support and 31 to 50 is 103. Oops, a little glitch with the pencil. And that's it. So it's really easy from a table. That's it for today. See you next class.